Problem 24, page 241. Here we have a particle of mass m equals to 5 kilogram is released from point A, I mean without initial velocity, and slides on the frictionless track. When I say frictionless, I mean we have a conservation of mechanical energy. Okay, so here, when we have F equals to O, we can say here E mechanical delta mechanical E equals to O directly. Okay, part A, we have to determine the particle's speed at positions B, C, B and C. Okay, we have to find the speed at B and at C. Okay, here we have m equals to 5. Here you have to put the reference of the system. Look here, we have 5, we have 3.2, and we have 2. So it's better to put down the x-axis and here the y-axis. Okay? In general, F equals to O, so we have mechanical energy initial equals to mechanical energy final. Here we have a system of only one object, so we can have the mechanical energy initial and final at any points in this isolated system. Here we have an isolated system here. We can apply M initial equals to M final at any 2 points on the system. Now I want to take this position when the ball was at this position is the initial position, initial state, and when the ball comes to this position, we can say the final state. I take state 1 and state 2, let's say here between when the ball at A and after when the ball is at B. You know, we have kinetic energy initial plus potential energy initial equals to kinetic energy final plus potential energy final between A and B. Okay, initially we have the ball at the position A without initial velocity, so we don't have kinetic. Initially, the object has a height equals to 5 meters, so we have mgh equals to 5. We don't have here elastic potential energy. We don't have spring. Okay, final state. In the final state, the object will be at the point B. We have to find the speed. Okay, at the final state, we have velocity. Okay, here we have VB. So we have a kinetic energy equals to have mVB square. And at this point, we have 3.2 meter height. So we can say we have mg times 3.2 meter. We can eliminate m, and m, and we can calculate easily VB. We can say here VB square equals to 2 times 5g minus 3.2 G. Okay, and here we can calculate a root like this. We get 2, and inside we have 5G minus 3.2 G. We have 1.8 G. Okay. Okay. Equals to, we have 2, 3.6 times 10 m per second. Okay, this is the answer about VB. I need to calculate its velocity at the position C. We can apply the same result. Let me write VB equals to 3.6. We can say here 36 m per second. Now we can apply the same method to calculate the speed at the position C. Okay. Here we can take 2 points, initial and final. We can take between this position and this position, and we can solve the problem, or you can take the system between this position and this position, initial and final, as we like. Let's take the system initially here between A and C. Between when the object is at the position A, we don't have kinetic and we have mgh. Okay, and when the object moves to the position C at this point, here we have velocity, so we have mv square at the position C plus mg. The height here equals to 2, mg times 2. We can eliminate m, and m. We can get Vc equals to 5G minus 2G equals to 5G minus 2G, 3, we have 660 m per second. This is the answer. I take the result in the case of a we don't have a contact between the object and the plane. In the case of a conservation of mechanical energy. Okay, we have a conservation of mechanical energy. I think we have part B. Part B, we have to find the network done by the gravitational force. We have to find omega done by mg in moving the particle from A to C. Okay, when the particle moves from A to C, I have to find this value. Here it's important because you have to know how can we solve this problem. What is the value of omega mg? We calculated its value before. We said omega mg and omega fs, okay, equals to minus delta potential energy, G. Okay, you have to remember this relation. Omega mg equals to minus the gravitational potential energy, delta, and in the case of Fs equals to minus delta potential energy elastic. Okay, here we have this case. Between A and C, you know here equal between A and C. C is the final position. So we have here the final value minus the initial value equals to uh, PEG equals to MGHC minus MGHA equals to minus M equals to 5 times 10 times HC equals to 2 minus 5 times 10 HA equals to 5. Okay, we get here minus 50, 2 minus 5, we get here minus 50 times minus 3, we have 150. Okay, we have 150 joule. This is the answer. You have to remember also this relation omega mg equals to minus delta potential energy, because you know here in general omega fc equals to minus delta potential energy. Fc can be mg or fc can be fs. Okay, in these cases, you can use directly omega fs equals minus delta potential energy. That's all about this problem.